Hello everybody. Today I want to explain you something related to the presentation which I want to have a talk in the Torino workshop in Perugia in Italy. Let me share my screen now. Yes, it's about AGB stars in globular clusters. You see here the lifetime of our sun, the age and luminosity. First, sun would be in our sequence, in the main sequence for the whole ages until around 12 billion years. Now, sun is here around 4.5 billion years, and it takes around 7.5 billion years that sun will move and leave the main sequence, and then it goes to RGB or red giant branch star, which in red giant it has helium in the core and hydrogen in the shell, but in the core helium won't burn, but hydrogen will be burning in the shell. And then the temperature is also low, and then the temperature goes up, and then in the suddenly in the stage that we call it helium flash, that it takes around a few seconds, the temperature goes up, and then in that time helium flash, helium in the core will be burned, and the core would have helium burning. And then the temperature goes down and it goes to horizontal branch stars or HBS stars. And then it goes to AGB stars or asymptotic giant branch star, which the core is smaller than the RGB red giant, but the temperature is higher. And in the core it has carbon and oxygen, but they are not burning, and it has helium shell burning, and it has hydrogen shell burning. And then it goes to thermal pulses. In thermal pulses, because we have different atmospheres, the atmosphere, for example, hydrogen and helium, they mix each other, and then the material goes out and they expel in the interstellar medium. That we call it thermal pulses. And here you see the phase and the age of them. For example, for asymptotic giant branches, so it takes about 5 million years. And then it goes to planetary nebula for 100,000 years, and the other age. What is asymptotic giant branch stars? As you see here, it is an AGB star or asymptotic giant branch star. It is one stage of the star evolution, and for the stars that has 1.8 to 3 solar mass, and the core is the size of the Earth, and it takes 5 million years. And it has helium, and it has carbon and oxygen in the core, but they are not burning. And then it has helium burning shell, and then it has hydrogen burning shell. Characteristics of asymptotic giant branch: convection in large portion of envelope, heavier elements formed in the star's interior, mixed, and by mixed we call it dredge up or mixed up. That it means that the whole star from the core until the atmosphere, they mix each other. A strong stellar wind, large radiation pressure drives the stellar wind. Particles absorb photons from radiation field. Interstellar medium enriched with mostly carbon and oxygen. Globular clusters. So what is globular clusters? Globular clusters are they are compact, and they are dense, and they have stars around more than 1 million stars in them. And in our Milky Way, the globular clusters have old and faint stars in them. And in the globular clusters for our Milky Way, they show the evolution and formation of our galaxy. Mostly globular clusters show the evolution and the properties of the galaxy that they host them. And globular clusters are associated with the mass and type of the galaxy. For example, they are related to low mass dwarf galaxy, and they are in the massive early type galaxy, that they are in the center of the galaxy cluster. And also we can resolve the globular cluster by numerical simulation. Different AGB stars in globular clusters. In the speed of AGB stars in globular cluster, they are sensitive to variation of light elements. Helium are typically larger than that expected in the photometric error. And we have lower metal enhanced star in AGB than in RGB. And in AGB or HBA, frequency correlates with the average mass of the most helium-enriched population. And we have multi-stellar population in globular clusters. In AGB, in globular clusters, that they are related to helium-enriched stars and mass. If the helium-enriched star has low mass, they won't evolve from HB horizontal branch to AGB. But if the enriched helium star has a higher mass, they will evolve from a horizontal branch to AGB star. Observing AGB stars in ultraviolet. Someone detected that in some AGB stars they saw a ring around some AGB stars, and they said that from first they detected in the infrared, and then they said that there is for example, a ring around some AGB stars. And there is a coincidence between the far and near UV and the detached dust shell. Someone said that the source of this detached dust shell is mass loss of AGB star. And then, for example, someone see for some AGB star or one AGB star that its name is HYA, and you see the image of that in here for far UV top panels and near UV bottom panels. Images of UHYA as discovered in the galaxy AIS image. The left panels show field source regions selected for removal. In right panels, field sources have been removed, and the best fit ellipse to the bright far UV emission is depicted by the dashed line. Variable AGB stars. Asymptotic giant branch variable stars are bright and the most distinctive individual star, and they are in old and intermediate age. We can say that they have large amplitude, and the period is more than 420 days, and they have some pulsators in them. Cyanogen chemical populations. Some scientists said that in some globular clusters, in most of them, if not all of them, They say that there are two chemical populations that they discovered first in early 1980s. The first is cyanogen strong and the other is cyanogen weak. And they are based on the observed strength of the cyanogen molecular bands. And you see here the spectrum of cyanogen, strong and weak. Effects of cyanogen AGB stars in globular clusters. Cyanogen strong stars seem to be disappear from when they want to change from RGB to AGB. And there is a variation in cyanogen strong stars that in some globular clusters seem that they have one mix of cyanogen stars, and but they are mostly have cyanogen weak. And it means that still cyanogen strong are less than cyanogen weak. Here you see NGC 288 and NGC 362. In RGB red and AGB is blue in both of them. And for RGB we have a mix of cyanogen strong and cyanogen weak. But for NGC 288 we have 100%, we do not have cyanogen strong and we just have cyanogen weak. But in NGC 362 we have also cyanogen strong and cyanogen weak for AGB, but still cyanogen strong is less than cyanogen weak, and we have mostly cyanogen weak. And you see here cyanogen weak and cyanogen strong is upper. These are the references, and thank you. Thank you for your attention and see you next time. Bye.